Hey to everybody and welcome to Apex YouTube channel Civil Engineer all over the world. And today we are going to talk about a very good topic, combined bending and direct stresses. Alright, when a body is subjected to axial tension or compression, a direct stress comes into play. When it is subjected to bending moment, then bending stress comes into play. Alright, therefore, if a member is subjected to an axial loading, a load in the direction of vertical, axial loading, along with transverse bending, a direct stress as well as a bending stress come into play. As an example, here, let's move to this example. Here we have a column with eccentric loading. So you can clearly see this is the column, this is the center line. Alright, then the load is not acting in the center, it has a small distance of E, so that is we call eccentricity. When you consider the plan view, you can clearly see the plan view of the column, and point load upside down P is acting in distance of E. Alright, and again when you consider about this retaining wall, this is retaining wall. Here its dead weight is acting in the direction of gravity, that is W1, and here you have soil. With that soil portion, another soil pressure is acting in this direction, this face of the retaining wall. When we consider the total of that, resultant force is acting here like this, but the force has a distance h in the soil backward direction. And this one, column with eccentric loading, we are going to consider this one. Previously I mentioned this one, column with eccentric loading. This is very much similar. You have a load like this, alright, P in E distance to the center line is very much similar. When you apply a load here vertical and another similar load vertically upward, then it's okay. It's very much similar to this one here, some kind of. Now using this load and this load with this eccentricity, it creates a moment, alright, and you have this point load. This means this can be all again similar to using these two loads and this distance. That part we can say a moment, and using this one point load, so we can say this one is again equal to point load plus again another moment PE. That's how we are simplifying. Alright, this means eccentric loading is finally similar to load in the center plus a moment equal P into E. So the stress diagrams, direct stress diagram is uniform. The stress is P over A, load over cross sectional area, and for this moment MPE, so you have the stress is M over I into Y. So you have diagram like this, that is bending stress. So when we considering the eccentric loading, you have a direct stress and a bending stress. Right, it is represented from these graphs. You can clearly see direct stress P over A and the bending stress M over I into Y, M over I into Y. So this total, we have to consider about the total. This can be simplified using the superposition theorem. When you add these two lengths will be added, but this is when in the other direction you have to subtract. These two will be added, then you will have this type of version. So the maximum thing is sigma max, small one is sigma min, minimum stress and maximum stress. So sigma max can be calculated P over A, that is the direct stress, plus M over I into Y, that is bending stress. So sigma minimum can be found P over A minus Mi over Y, direct stress minus bending stress. Sigma max is direct stress plus bending stress. So for a rectangular section, this I I can be calculated 1 over 12 into BD cube. 1 over 12 into BD cube. This is a standard equation for rectangular section in order to determine the value of I. So y can be found, y is equal to d over 2. So let's consider about this example. A hollow rectangular masonry pier is 1200 mm into 800 mm cross section and 150 mm thick. Alright, a vertical load of 200 kilonewton, you can clearly see 200 kilonewton here. 200 kilonewton is transmitted in the vertical plane bisecting 1200 side and at an eccentricity of 100. Eccentricity, there is a eccentricity 100 mm from the geometric axis of the section. So calculate the maximum and minimum stresses developed in the section. We have these two equations for sigma max and sigma minimum. We can use those for these calculations. Alright, I'll zoom out a bit. Now you can clearly see. Right, this is the column, this is 200 kilonewton, load eccentricity is 100 mm. This is the center. When you consider the plan view, you have a hollow thing here. Now this is the load, this is the eccentricity, these are the dimensions. Alright, so sigma max equation is direct stress P over A plus bending stress M over I into Y. So A is 510 to 10 to the power 3. So direct stress sigma can be P over A is 0.39 Newton per millimeter square. And the bending stress is M over I into Y. So we can substitute the value. I is found 1 over 12 into BD's cube. So it's this much. And Y is this much, 800 over 2. So we can substitute the value for bending stress formula. You can find 0.19 Newton per millimeter square. So this is direct stress value, you can clearly see it. This is bending stress value, the smaller one. Now you can find the draw the graphs. This is for direct stress 0.39, this is for bending stress 0.19. So this is a small one. So in this edge 0.39 minus 0.19, you will give resultant for 0.2. This edge 0.39 plus 0.19, you will give 0.58. So this is the maximum stress and this is the minimum stress. Very straightforward calculations. And when you consider symmetric column with eccentric load in about two axes, so it can be happen by x-axis. You can have the eccentric load. By y-axis you can have right here. By x-axis you can have eccentric loading. In y-axis you can have eccentric loading. Right. First one, direct stress on column P over A. Direct stress is straightforward, P over A. So you have two directions, bending stress due to eccentricity x. So that is M over I. This one, M over I into Y. M over I into Y is this one, Px over I into x1. So bending stress due to the other y-axis, so that is M over I into Y is Pe by Y by Y into Y1. So total stress can be found P over A, direct stress plus or minus bending stress due to eccentricity of Y, bending stress due to eccentricity of x-axis. So the summation. Alright. Then we have to consider about limits of eccentricity. So you can talk about limits. When an eccentric load is acting on a column, it produces direct and bending stresses. If the bending stress exceeds the direct stress, alright, now we are talking about a limit. If the bending stress exceeds the direct stress, then there will be tension on one side. So if the tensile stress is not permitted, then what will happen? Sigma bending should be less or equal than sigma direct. Bending stress should be less or equal than direct bend stress. So we can consider this type of thing. You can have so many loads in X and Y. So what you need to do, sigma bending should be less or equal than sigma direct. So you can substitute your known parameters. Then you can ZD is I over Y. This is elastic modulus. The definition of ZD is elastic modulus, that is I over Y. So you can substitute it here. You have I over Y here, so you can Z, I take it here. Now you can eccentricity can be subjected, then you will come up with eccentric should be less or equal to Z over A. Z is elastic modulus and A is the area. So this is a kind of requirement for tensile stress is not permitted. So if the tensile stress is not permitted, E should be less or equal than Z over A. So you can use this equation. When you consider a rectangular section like this BD, then Z can be found using the previous equation. A can be found, then you can find E by substituting to this formula. You can find E. And the load can be eccentric on either side of geometric axis by amount equal to D over 6. If the line of action of the load is within the middle third as shown above, then the stress will be compressive throughout the section. That is called middle third rule. Alright. Now we consider about a hollow rectangular section. BD, this is a hollow rectangular section. Now Z I over Y. Z can be found using this equation. So for no tension requirement, what should happen? E should be less or equal than Z over A by using this formula. So you can substitute these two values here and you can find a relationship. When you consider a solid circular section like this, so D and D over 4, then Z can be found 5D cube over 3, 32. A is can be found 5 over 4 D square. By substituting in this formula, you can find a relationship for E eccentricity, that is 8 over A into D over. So for what thing is this thing needed? So this is for tensile stress is not permitted. For not permitting the tensile stress, eccentricity should be less than this value. That's what we are finding. Again, we can consider another example from hollow circular section. This is hollow circular section with capital D and simple d. So here X Z values can be found using this one. A is can be found using this one. For no tension requirement, you can substitute the values in the previous this equation. Then you can find a relationship for this one for no tension. So let's consider another example. So wind pressure on walls and chimneys. Right? Walls and chimneys are subjected to wind pressure, which causes some bending stress at its base. This is the chimney. So its height is h. Its load is this is axial force, bending moment, and horizontal load. A masonry chimney of hollow circular section has external and internal diameter of 2 meters and 1.5 meters. It is subjected to horizontal wind pressure of 1.5 kilonewton per meter square. Determine the greatest height of the chimney if no tension is allowed at base in order to not generating the bending. The tension here, you have to find the H at base. The unit weight of masonry is 20 kilonewton per meter cube. We can shift the solving the problem. So this is 1.5 horizontal the wind force, and here this one is the plan view of the chimney, 1.5, and this is 2. This is the horizontal force. So we can determine I. I is 5 over 64 into 2 to the power 4 minus 1 to the 1.5 to the power 4. This is from the equations for I, that is 0.54 meter to the power 4. 0.45 meter square. Z is 0.45 meter square. Okay. And A is 1.38 meter square. So direct stress due to self weight, sigma 1 P over A direct stress, HR over A will be simplified HR. So that is equation 1. So bending stress due to wind, that is sigma 2 Mi over Y. You can substitute the values here, and this is the expression for that one. Gamma is unit weight, that is 20 kilonewton per meter cube. So when we consider these two expressions, both are with H and R, so sigma 1 will become larger than sigma 2. So from 1 and 2 we can say H is equal, by simplifying those, H is equal to 7.2 meters. So subscribe our YouTube channel by pressing the button here, and hang with us for more YouTube videos about civil engineering and structural engineering things. Bye for now.